Hello. Today I'm going to talk about the effect of natural aging on the tensile properties of PETG-CF filament. This is only the first results of the ongoing project because we have imagined to be very large project. Because of that, I have to, I don't know, 15, 16 slides here and to present to you only the first insights in tensile properties as we named the presentation. My name is Nenad Milošević, as a colleague said, and here's the abstract. So on the end, on the acknowledgement, you can see that is the part of the bigger investigation and only small portion of the results regarding the tensile properties of the aging PETG is presented here. So, okay, for the start, let's say that parts manufactured using additive technology have been excellent choice for prototyping for some time now, and many companies, firms, and research centers, or so on, doing this, doing prototyping by additive manufacturing, and PETG is a very common choice when you use from the different filaments for this type of parts. These materials, PETG, demonstrated significant plasticity and toughness in the filaments. So we can say, because sometimes has the ability to form the neck during the tensile test, we have said that is some similarities to metallic materials. Consider all above, the question arises as to whether PETG can be used for manufacturing structural elements for smaller loads and indoor conditions, because not only the parameters that we have in the lab on the results that we get in lab, so the tensile properties and so on, not only that is what's the difference. Can we use them or not in the indoor conditions? Okay, but for a longer period of time. Does we get degradation of mechanical properties after some time or not? And can we use that as the structural elements for some applications? Because of that, we want to try to analyze the aged samples for 300 days. In our cases, in natural aging. So you can see. In addition to standard tests, which have been performed many times, the questions of aging has also emerged, the degradation of mechanical properties of manufactured parts after a certain period. Aging PETG parts can lead to significant changes in mechanical properties, such as embrittlement, decrease in tensile and compressive strength, particularly from exposure to UV radiation and moisture. And because of that, we want to start our test or our project. This work analyzes the change in tensile strength between new samples and samples manufactured 300 days ago from the same PETG-CF filament. CF is for carbon fiber reinforced filaments, because to get better strength and something like that, but it can also emerge from the ductility. Accelerated aging at a temperature of 60 degrees Celsius is commonly used based on time-temperature superposition. So this temperature maximizes aging rates in traditionally manufactured PETG. That's the common sense you can find in many papers, but our opinion is that 60 degrees Celsius is high temperature for filaments and for polymer materials. So we do not want to do this, so we do it natural aging manner. Papers present this type of aging showing an increase in both strength and ductility for some PETG materials after aging for a time period equivalent to 30 to 300 days at 25 degrees Celsius, and we want to check that. Although print conditions are commonly optimized for mechanical performance, long-term aging behavior needs to be understood to ensure reliability of additively manufactured durable goods through their expected lifetime. This is also taken from the work, some paper, and it's a very good sense. So we take that also as the start of our project. Aging at temperatures above 50 degrees Celsius produce better adhesion between layers in manufactured parts, which results in increasing strength. But this type of treatment is closer to thermal treatment than the aging. So because of that, we will look at that like thermal treatment. After performing this type of treatment, the parts should be naturally aged, after which their mechanical properties need to be analyzed so we can see after some period of time, does the parameters go down, decreasing, increasing, or what happened with the part. Because PETG printed parts are suitable for indoor use, we evaluated their mechanical properties after aging under ambient conditions. So we know that exposure to UV lights or something like that, will get to the degrading or decreasing the parameters. So we say that the PETGs can be generally used for indoor applications. For this print, PETG filament with carbon fiber reinforcement profile is used on the bamboo printer with 0.4 millimeter nozzle and 0.2 millimeter layer height. This is the look of the printer, the standard printer with the enclosed chamber for the thermal stability during the print. The model is configured with three perimeters, so it's been 3 walls, 3 top layers, and 3 bottom layers, along with almost solid infill, 99% of infill, which provide the test sample with higher strength and so with higher possible strength. The nozzle temperature is set to approximately 255, while the heated bed runs at about 70 degrees Celsius, ensuring good adhesion without excessive material bleeding, and approximately 5 millimeter beam is enabled for improved bed adhesion, and supports are disabled as the geometry is self-supporting, printing flat on the table. Print speeds are tuned so the outer wall runs slow, around 60 millimeters per second, to achieve a better surface finish, so we can get most of the part, while the inner walls and infill operate much faster, 250 to 270 millimeters per second, to reduce total print time. This is done in accordance to be closest to the real scenarios, but because of that, it will be much faster infill. The part cooling fan is significantly reduced for a max around 40%, to avoid overcooling and brittle behavior of the gathered parts, whereas the chamber exhaust fan runs at a moderate level to maintain thermal stability within the enclosure to be much best adhesion between layers. Overall, the settings are relatively aggressive in terms of speed, yet well balanced to produce a strong, nearly solid PETG samples with a consistent and clean external surface qualities. Samples dimension we choose to get according to ISO 527.1 and 2. This is the dimensions according to the standards in millimeters. So we can see that gauge length of the 50 millimeters. So we will use that in the primary test. 6 samples are naturally aged for a period of 300 days in the room conditions, as we also said, but said it again, is not harm. Okay, so the looks of the new samples are presented here, and after 300 days, this is that 6 samples, so we can see that the dimensions and the shape and everything is the same, but the totally of 12 samples are tested. Testing was performed on the tensile test machine, universal testing machine. We use mostly for metallic materials at 100 kilonewtons maximum force, and because of that, because of the big maximum force, and because of the standard, also we produce testing by stroke control, then set to 1 millimeter per minute, because we want to get precisely result as can in terms of force and in terms of deformations. Extensometer with 50 millimeter gauge length was used, and tests were conducted at room temperature. This is the setup of the experiment, and this is the close-up one, so that we can see the extensometer of 50 millimeter gauge length and machine on which the test was performed. After the testing, we get these type of fractures for the new samples and from the aged samples. And from this picture, you can't see much of that, but we can see that in new samples we have the deformation stripes on the many samples that on aged we only have on one, only for 4 samples. Here the stress strain curve. Only one sample aged on the sample number 4 has the slightly better results than the rest of it. The rest 5 of it also the same. And we have when we get average values, we get maximum force of 1,000 newtons, ultimate tensile strength about 27 megapascals, and maximum deformation about 3.85%. What we can see here, that's the common behavior of the PETG, nothing new. But if we had look on the diagram for the new samples, we also can see that the maximum force is also around 1,000 newtons, ultimate tensile strength about 28 megapascals, and maximum deformations about 4.76. And also we can see that two groups of specimen are diverse, so to say. So when we compare these results, what we get on the one table, so we can see and compare them. We only can see that for the maximum force is not the bigger difference. Also is integral tensile strength. Only difference is for the deformations. So we can conclude that the results suggest that the strength of aged samples differs only marginally from that one new ones, indicating that natural aging has no significant effect on the strength of PETG carbon fiber reinforced parts, which are not thermally treated before aging. In contrast, the reduction in ductility is considerable. The observed decrease in ductility during aging is most likely attributed to moisture absorption from the ambient environment, so we can increase in brittleness. Aging of polymetallically fabricated parts at temperatures above 50 degrees Celsius can be interpreted as thermal conditioning rather than true aging. And further research should address the observed reduction in ductility over longer natural aging intervals in both thermally conductive and as printed PETG-CF components. So we can compare them and see if there's a difference. Thank you for your attention. If you have any questions.